We now would like to begin the general proof of Gauss's law. And because this will require many steps, let's just make the statement here of what the general statement of Gauss's law is. If we look at the electric flux through any closed surface, doesn't have to be spherical, let's call it S, then this is equal to the charge enclosed in that surface. So we'll just write this out in words, charged enclosed divided by a constant epsilon naught. And this has the name of Gauss's law. Now, in order to prove this theoretically, we've already shown it's true for a single charge in a spherical surface, and our next step is the following. Suppose we have a charge Q, and I'm just going to do a little drawing here. I'm going to create a closed surface that looks like this. So this just takes a little bit. OK. Now, my closed surface is defined by this solid angle. And let's now look at a few aspects of this. For instance, because this is a closed surface, n was always outward. And so here we have, I'm going to call this n hat 1. This surface here will be 1. And on this surface, because it's point charge, and let's just make our charge positive. That way, our electric field points away. And we have an electric field that goes outward. That goes like E1. And on surface 2, our electric field is not as big because of the inverse square. So that's E2. But the unit normal also now points outward, n hat 2. So right away, we see that if we want to calculate the electric flux through these two areas, and let's call this A1, and this one is A2. So the electric flux through this particular closed surface, E dot n hat dA. Now here's the key thing. Because the electric field is antiparallel to the outward pointing unit normal in this closed surface, our first piece is minus E1 times A1. And remember, E is pointing radially outward, so it's perpendicular. We're making this very small, so we're not worried about any deviations of E being non-uniform. This is a very small solid angle. And on the second one, we have both E and the unit normal are pointing in the same direction, so we have E2, A2. Now, what we know for a solid angle here, a very small solid angle, that the areas, the ratio of the areas here, and if this is a distance R1, and going out here is a distance R2, then the ratio of the areas goes like the distance squared. And the ratio of the electric fields goes like the inverse distance squared. So we have 1 over R2 squared, 1 over R1 squared, which is R1 squared over R2 squared. And now what we see when we calculate the flux, let's write that out. Through the closed surface, we had E1, A1 plus E2, A2. And now let's make our substitutions. And over here, we're going to make the following substitutions. We'll have for E2, E2 is equal to E1 times R1 squared over R2 squared. And A2 is equal to A1 times R2 squared over R1 squared. And now you see that all the radiuses cancel here. And the reason this is working, remember, is precisely because the electric field is a 1 over R squared field. And what we're left with is minus E1, A1 plus E1, A1. And we get 0. And so this was our first step. Through this wedge with a fixed solid angle, the electric flux is 0 when the charge is not enclosed. And again, the reason was that the flux was negative on this face and positive on that face. And now what we'd like to do is start to generalize this for an arbitrary surface, closed surface.